So our next speaker is Yunzhu Li. Yunzhu is a assistant professor at Columbia University, and his work tries to end the robot with the capability of perceiving and interacting with the physical world, and it tries to do that leveraging structured world models and multimodal perception. Prior joining Columbia, he was an assistant professor of University of Illinois Urbana-Champaign. And he also spent some time as a postdoc at Stanford, and he obtained his PhD at MIT, advised by Rusty Drake and Antonio Torralba. So, Yunchu, the floor is yours.
Okay, thank you, Alberta, for the very kind introductions, and super excited to be here. Talking about a series of work we have been doing on trying to simulating and manipulating deformable objects, especially with structured word models. So the first half of the talk will be actually a review of some of the things we have been doing over the years, especially using graph neural network on modeling the dynamics of deformable objects. And the second half of the talk will be about like some of our recent developments on trying to identify the right recipe of modeling and building the digital twins for deformable objects. So specifically, like the key questions we're hoping to answer is, want to arrive at this kind of human level manipulation capabilities. Whereas many of the existing like manipulation systems in the real industrial situations are still like manipulating, for example, boxes. Like you are in academia, you probably have seen many interesting like robotic videos, like robots working with like interesting stuff. But if you ever went to any of this kind of industrial like shows, for example, ProMat or Ultimates, you'll be amazed how many boxes you will see. Just oceans and oceans of like perfectly shaped boxes where people are moving around. Those are the current reality of what's actually deployed in the industries, which are still very like far away from what we really want the robots to do. For example, humans can do like many like deformable object manipulation tasks at a very high performance, like cracking eggs, bread butter, making bread, making sushi. And one of the key enabling factors is this kind of intuitive models of the world. We learn from our interactions and predict how the environment is going to change if we apply a specific action. For example, how the dough will deform and how the onion pieces will move around. And when we, for example, like when we apply our actions, and we can use that predictive capabilities to plan our behavior. So in general, like this framework works like this. You give this world, you have this planner. This planner will take in the observation as input, and internally, we have this intuitive model that predicts the evolution of the systems under some like novel actions. And then we can plan our behaviors based on this predicted outcome. In order to build this kind of predictive models, there are generally like two ways of doing it. The first way generally people currently have been thinking about is this what's called like 2D word models, this pixel like conditioned like action conditioned prediction models. Generally, they map something, the visual observations, into the latent representation and learn dynamics model over that latent space. The nice things about these lines of work is they can learn directly from partial observations and handle systems where the underlying dynamics are uncertain or unknown. We have success stories like Moser rows, like many other like examples. And the key issues of these lines of work, it considers the environment as unstructured, and it's very limited in terms of generalizations. So when thinking about those or a pile of coffee beans, we're not thinking of them as just one latent vectors. We have some very structured understanding about this relationship between different components within these dynamical systems. So the other way of building these dynamical systems, especially leveraging structures of the environment, is based on our understanding of physics, like F equals ma. This is what Chuang was talking about on using physics-based engines to build the dynamics models. So this is arguably the most compact way of building this dynamic model and has excellent generalization capabilities. We also have many success stories. But the key issues of deploying this type of model in the manipulation domain is that this model requires full state information of the environments. And sometimes full state and parameter estimations of the environments is just very hard or sometimes impossible, like the examples I showed here. So on the left is model learning. On the right would be structures in the model. So my goal is really trying to bridge the gap and get the best of both worlds and trying to learn model from the robot's interactions with the environments and with structures inspired by understanding of physics, by understanding of geometries, and using this learned model for us to do better physical interactions. So let's make the problem a little more specific. Here is the objective function we hope to optimize. It's the objective function defined over the observation y and the action u. So we have to think through three most critical constraints. The first one is perceptions, which essentially maps the observation into some representation z. And then is a dynamics model. So given the current z and actions, want to predict the evolutions of the systems. And then want to derive the action signals conditioned on the current representation z. So if you look at this kind of formulation, you'll realize that the choice of representation z plays a very important role in deciding the overall structures of the systems. It's very important for us to carefully thinking like what type of z should we use and how we can choose the suitable z's that give us the desired levels of generalizations and sample efficiency. So for many of the work we have been doing so far, we use the representation of particles, which essentially describes the whole environment using a bunch of points. Points describing the overall geometries and interaction both within an object and, of course, different objects. So to model the dynamics of this particle systems, we use graph neural network. We call it graph-based neural dynamics models. Essentially, given a graph of 3 nodes and 3 directed edges, our representations of this environment will be the node set V and S set E. And for every edge pointing from B to A, we aggregate the information from the sender and the receiver to derive the representation on that edge E. And then for all the nodes, we will aggregate all the representation on edges where node A is the receiver. So we'll update the representations on the node A. Then we can define all the objective functions based on the either edge representations or the node representations to do the supervision. Here what we care is about the evolution of the system. So we predict the evolutions of the systems by minimizing the mean squared error between the predicted next state and the actual next states. Of course, the node encoder is shared among all nodes and edge encoder is shared among all edges. So that's why we choose graph neural networks, because this has some very nice internal structures that allows us to do very sample efficient learning. So by learning this model, we'll be able to model system. For example, here are examples where 2 fluids fall down and merge with each other. The left is the ground truth. The right is our model's open loop future predictions. Here's another example of mimicking a parallel jaw gripper of deforming class systems. Here's another example of shaking a box of fluids where we control the movement of the container. And our learned dynamics model matches very nicely with what the ground truth shows on the left. And because the node encoder is shared among all nodes and edge encoder is shared among all edges. So the learned model can naturally generalize to systems that are larger than during training, that is 2 times fluid examples. When moving to the real environments, we'll be able to, for example, build some kind of perception systems, do some kind of reconstructions of the objects, can also assign this kind of graph representing the overall structures and overall shape of the environments, both for the rope, for the granular objects, and also for the even for rigid objects. By representing these real objects using graphs, we'll be able to, for them, model their dynamics and even learn the dynamics model directly from the real-world interactions. So in one of our earlier works, we try to tackle this very complicated dumpling making tasks by directly learn the dynamics model from real-world interactions for the elastoplastic object like class systems. And we equip these robotic systems with 15 3D printed tools. And then using 4 RGBD cameras looking at the environments to do the reconstructions of the dough and plan the robot's behaviors within this kind of red regions of interacting with the dough. And the learned systems really benefited from the use of graph-based neural dynamics models. Because of these very nice structures we use, we have shared encoders for both the edges and nodes. So we allow very, very simple efficient learnings, where for each tool, we only require 20 minutes of real-world interactions, and we can have sufficient data for us to learn pretty decent dynamics models for the modeling of the dynamics of these objects. And this learned dynamics model is noticeably more accurate than the state-of-the-art deformable object simulators like material point methods, even if we apply very extensive system identification. So here is actually the visualizations of the model's predictions and our representations of the environments. Here, the blue points representing the representation of about the geometry of the dough, and red points describing the geometry and our representations of the tool. The first row representing our model's open loop prediction, and second row is the ground truth. You can see our model's prediction closely aligns with what happens in the real environments. Here's another example of the dynamics of a pusher, another examples of the rollers. We can successfully predict the size and the area of the dough will be enlarged as you apply this kind of rolling operations. And here's actually the actual executions of the robots using this kind of neural dynamics model. So what's interesting about this video is that there will be a person constantly perturbing the robot from doing its job. And the robot has to give the current observations of the environment and reactively and dynamically selects what tool to use, which is a decision made at the discrete level. And given that specific tool, the robot has to also decide what specific continuous action to make in order to progress into the next task stage. So this is actually this two-level planning, both at the task level and the motion level, for the robots to be robust to this type of external disturbance. Like I mentioned earlier, the key enabling factor is really this kind of neural dynamics model of this dough that predicts how the shape of the dough will change if you apply a specific actions. And this forward prediction model can allow us to design this kind of predictive, this kind of planning systems that is able to progress over this kind of dumpling making procedure. Here's what's really interesting. After the robots have enough area, the humans cut a circle and humans choose no mercy, destroy everything. And the robot knows it has to start from the very beginning in order to be robust to this kind of external disturbance, which shows the robustness for the robots both within a task stage and across different task stages, and for the robots to actually solve this very complicated long horizon deformable object manipulation task. In the end, the robots will move the dumpling skin on top of this dumpling clip and move this dumpling fillings on the skin and close the dumpling clip in order to make a dumpling. So this, I would say, is a very, very challenging task, especially using this general purpose robot arms equipped with general purpose 3D printed tools. We actually apply this very similar techniques like this neural dynamics model, this graph-based neural dynamics models, also on many other deformable objects. Here is an example of trying to do granular object manipulation. We're still using the same a graph representing the foregrounds of this object piles, and using this graph-based neural dynamics model to predict how the granular pieces will move around if you apply a specific actions. And then we can use this forward model to plan the robot's behavior to rearrange these granular pieces to achieve complicated target configurations. You probably have already realized the target configurations are all the letter shapes from letter A to letter Z. This is a highly non-trivial task because it involves some redistributions of the object masses and also some fine-grained alignments of the object pieces with the targets in order to do this manipulation task. And again, exactly the same framework, this kind of graph-based neural dynamics model can also be applied to multi-object interactions. Here's another example shows you can actually learn this graph dynamics model to predict this multi-object interactions for this kind of stowing task and be able to stow the objects on top of this kind of shelf. So to summarize a little bit of the first half, the take-home message so far is that we use a combination of particles and graph neural networks that is able to model objects dynamics, especially for objects that are compositional and with high degrees of freedom. It handles elastoplastic object, granular media, and also multi-object interactions in the real environment. It comes with two key benefits. The first benefit is about generalizations. Specifically, we can generalize to systems that are even larger than during training, like the fluid examples, or a target configurations that are never seen during training, like the A, B, C, D, E, F, G, those letter shapes, because the training data are actually just randomly pushing actions on these object piles. The second key benefit is about sample efficiencies. For example, in the dumpling making one, all the models are learned from real-world interactions. And for each tool, we only require 20 minutes of real-world interactions, and that's sufficient data for us to learn a very accurate dynamics model, noticeably better than any physics-based models out there. And this lines of work actually inspired two lines of follow-up works, especially on learning large-scale, dynamical systems based on graph representations. Here are just some interesting work on intuitive physics, batch-based systems, etc. This is on, for example, the graphics and the intuitive physics domain. And on the deformable object manipulation domains, here are just some other follow-up works that really trying to also extend our framework, this graph-based modeling on many other deformable object manipulation tasks. So then, after we have done all of these works, we essentially have this tool, this graph-based neural models, that we have this kind of hammers. We try to identify all the nails we can have. And this is what we have been doing so far. And we want to extend beyond that. Specifically, what's next is really trying to thinking about, obviously, more complicated tasks and more complicated objects, especially not just with like one type of objects, but heterogeneous objects interactions. And we want to scale up not just like on the tabletop domain, but on the way until this kind of in the wild data. Example like OpenX or Droid. And obviously, we want to build this type of engines, this kind of like a forward prediction model that can act as either data generation engines or evaluation engines, which can come hand in hand and can be very, very handy for the current developments of, for example, vision language action models. So looking back, we're actually like navigates over this kind of spectrums. On the left will be more physics, on the right will be more learning. And our graph-based neural dynamics model is somewhere in the middle. And on the left end, for example, on the physics side, there has been a lot of like physics-based simulators. Chuang have mentioned their Genesis, and also NVIDIA Warp, which is also described, for example, the physics-based modelings of the environments. And on the very end, on the right, will be this kind of learning routes, where people have been doing like a 2D, for example, action condition video predictions, and trying to generate those videos and see how far we can push from there. So obviously, they all have their pros and cons. I don't want to reiterate them. But I also want to see, like, are there any opportunities in the middles? Do we have the right recipes that can marry the benefits of the structures, but also is easy and accessible for us to scale things up and be able to apply it all the way into the, in the wild collected data? So our trials, for example, more on the physics side, is this work called phase twin, which is essentially trying to use some kind of physics-based priors that enable us to build a digitalized versions of deformable objects that is both sample efficient and generalizable. So what we are doing here is that given a few seconds of real-world interactions shown on the left, we can reconstruct a digital twin of this object. What we mean by digital twin is both the geometry, appearance, and also the dynamics of that object. And in the middle, what we're showing is our reconstructed geometries, and all the points on this kind of geometry are also tracked over time. And the points on the human hands represents the actions we are reconstructed also from this video. And the right video actually shows our resimulation results overlaid with the original videos. What we mean by resimulation is we only take the first frame as input, replay the actions reconstructed from the video in an open loop fashion on our digital twin, and we do action condition 3D video prediction. And we overlay that video with the original video. You can see it aligns very, very nicely with the original video. And here's like overall how the framework look like. Like the optimization is done both on the geometry, motion, and also the rendering loss. That represents this kind of object using a physics-informed modeling, specifically like spring mass modeling, that trying to model the dynamics of that object and using Gaussian splattings to model the appearance. And obviously, after we have these digital twins, you can just apply any novel interactions. And for example, here we have this kind of keyboard interface to do real-time interactions with this like deformable objects. It also applies to many other objects like stuffed animal, clothes, ropes, etc. And in the robotics domain, we actually do real-time data collections about the robot actions and replay these actions both on the real robots and also on our digital twins. They are happening all at the same time. The left shows what's happening in the real environments, and the screen shows what happens in our digitalized environments. And this video essentially shows two things. One, our digitalized clothes is very accurate. The rendered video aligns very nicely with what's actually happening in the real environments. And second, our predictions is in real times. There's nearly no delay between our models' open loop predictions versus what's happening in the real environments. So this is because we implement everything using NVIDIA Warp, which can benefit from GPU accelerations. And we have also been pushing this direction forwards, trying to build this digitalized digital twin of this environment for this entire interactions and manipulation cycle. Here we replay the exact same action trajectories, both in the simulation and real environments, and they align very nicely with each other. The left is the simulation, the right is the real environments. And using this model, obviously what we can do is to do model-based planning. Here we show an example where the left is the target states, the right is our planned trajectories executed on the real robots based on our digitalized rope. Here's another example where the robot has to come up with some motions to do this kind of like folding behaviors to fold the clothes that matches the target states. And obviously here, like we actually did some kind of constraining of our action space in order for the search to be effective. But overall, we're just showing that our model actually very nicely matches the dynamics of the real world that is able for the robots to do the motion planning. So on the left is actually more physics side. We're also trying to move forward and trying to see if there's kind of more learnings we can blend in for more scalable, like scale up of this framework, which actually enters our RSS paper this year, which gonna be presented, I think, actually tomorrow or the day after. It is particle grid neurodynamics models. So remember, like earlier, I showed this video where we use graph as a representations to like model objects of different like geometries of different like materials. And actually, there are some like very obvious limitations like as we like going through this process. Specifically, it actually requires expert knowledge in how to do the graph constructions. Like sometimes the graph actually has to be constructed very carefully. Like the edges cannot be too dense or edges cannot be too sparse. We also need to have the right attributes on top of the edges and also the nodes for it to work effectively. And sometimes insufficient message passing steps would also fail to capture the global informations, especially if the graph is sparse or like disconnected somewhere in the middle. And it still is a little bit limited in handling partial observations. More or less, we still assume to have reasonably complete geometry of the environments. So for example, for the dumpling one I showed earlier, although we only require, for example, the surface of this dumpling, but still we need some reasonably complete description about the geometries of that dumpling. So that is why we built like these systems called particle grid neurodynamics model. It really is a method inspired by material point methods, where we not only relies on the particle representations of the environments, but also consider the grid representations of the environments, where we have this kind of point encoders and also this implicit like fields that is able to do this kind of grids like velocity decodings that's to do this kind of particle to grid transformations and grid back to particle transformations in order to predict the dynamics of the movements of each and every one of the particles. So essentially, this is a hybrid representations, and we are doing this particle to grid and grid to particles process to like marry the benefits of both the grids and also the particles. And what we need really is just in this case, a few minutes of real-world interactions. And Kaifeng here is actually just doing random interactions with this rope using this robots. And these interactions will be collected. And we will be first reconstructing the appearance and geometries of this rope. Here we are using Gaussian splattings. And then we'll be able to do action condition 3D radio predictions. Here on the top right is our actually a keyboard interface to model the behaviors of this end effectors. And this end effector is being end effectors movements is being real-time recorded and played on this kind of rope. And we'll be able to predict both the end effectors motions and also the rope's motions for this kind of 3D action condition video predictions. It also applies to many other objects like clothes, stuffed animal, and also boxes. For people who are familiar with dynamic Gaussians, I want to emphasize this is not dynamic 3D Gaussians. This is action condition 3D video predictions. Dynamic 3D Gaussian is essentially like a temporal interpolation. But here what we are doing is actually temporal extrapolations of imagining how the environment is going to change when you apply novel interactions on top of this object. So this is what we investigated so far, meaning we have a very strong emphasis, as you can see, things has to work in the 3D. If there are structures we can incorporate into the systems, we should incorporate that structure into the systems. And I have this belief that currently people are doing large-scale data collections for training this vision language action models. And many of this data, if you only using them for policy learning, that would be such a waste. Because there's a lot of very rich dynamic information that's embedded inside those large-scale collected data. And what we need for training those policies is action condition robot interaction data. Now, if we need to train this kind of word model, is also action condition robot interaction data. So those data can actually be very, very nicely like used for us to obtain this world model that can be very, very beneficial for us to develop policies. Where the policy and model are just the two sides of the same coin. One is the forward process, which is the model, and the other one is this inverse process, which is the policies. So I'm personally very excited about the developments of the world model. It's just that we are still trying to identify the right recipe, the right amount of structures that is able to give us the generalizations and the sample efficiency, but at the same time can utilize all the in the wild collected data people are doing nowadays. So in the end, I want to thank all the collaborators, especially the lead students like Han Xiao and Kai Feng for the remaining two works. If you have any questions, you should definitely chat with them. They've been doing amazing works. Without all the sponsor agencies and the collaborators, it would be impossible to do all these works. And I'm happy to take any questions now. Thank you.
Thank you, Yunzhu, for the great talk. You did amazing work and very extensive work. So one quick information before moving to the Q&A, we will also take the last oral presentation before the short break. Sorry for that. Having said that, do we have any question from the audience? Okay, maybe I can start. I think you've shown impressive results of especially digital twins, neural simulators. I wonder, how does this work with very highly dynamics movement, like for example, flinging, interactions with the object? Because what you have seen, you have shown, seems like more slow movements. So any thoughts on that?
That's a very good question. So for more dynamic motions, so in general, one of the key limitations I would say is about the current, our means of doing visual trackings. Because for the identifications of many of the model I showed here, we actually require some kind of tracking about the motions of the object. It doesn't have to be complete full state tracking. It only needs to be a partial trackings. Which is nice because there has been a lot of development on the visual foundation model sides. And many of the development on that side can actually be very nicely integrated in many of our work. For example, Phase Twin is benefited from not only the visual tracking, but also the single image 3D reconstructions. But that I would also say is one of the limiting factors, because if the things move very, very fast, very, very dynamically, you create motion blurs. That will create issues for those visual trackers. But I believe over time, that's just going to become better and better of doing tracking over these highly dynamic scenarios. Having said that, for example, for system that was a more physics-based prior, for example, this Phase Twin, even our identification process works in regimes where the movement are reasonably slow. But because we have physics priors, this kind of identified model can actually be used during the test time in high-speed regimes.
Okay, thank you.
Thank you.
Do you think this could be maybe a sensing issue? We keep using RGB. Of course, RGB has a lot of information, but there exists also event cameras, right, which are faster, providing information and give information about the flow. So do you think we should really stick with RGB, or other type of sensing, or depth sensing could be the way to make it faster at least?
Yeah, that's a good point. So for many of these works, we actually use depths for 3D reconstructions. But you bring a very interesting point of using event-based cameras. So we haven't really done those, but I think that could be a very interesting directions to explore, especially you mentioned, those high-speed regimes, especially when you do high-speed trackings. And I think those sensors can actually be very useful in those scenarios.
Okay, let's thank again our speaker. Thank you.
Thank you.